Okay. Last but not least for this session, it is my pleasure to introduce Grant Johnson from Princeton University. He had two practicums, one at Los Alamos National Laboratory and the other at Lawrence Berkeley National Laboratory.
Hi, I'll be talking to you today about discontinuous Galerkin algorithm for particle kinetics on smooth surfaces. So I'll first describe some of these points to explain what does it mean to have particle kinetics and then a discontinuous Galerkin algorithm. So my overall thesis goals here, I want to evolve a system of particles in a complex geometry, and specifically I want a kinetic description. What does that mean? So this plot to the right is going to show the density on the surface of a sphere. We end up having the contour of it show essentially how dense some place is, from most dense to least dense. But when we have a kinetics description, we don't just describe the density. At each point, we have a fully separate velocity space. This can take any sort of form, and this is our velocity in the theta direction and velocity in the phi direction. Now, if the difference between a fluid and a kinetic isn't clear, it'll be on the next slide. But the reason that we want to do this and what we're working towards, we're motivated by working towards a totally general relativistic framework for this sort of evolution. So let's describe the differences between a fluid and kinetic approach. So in a fluid approach, you have these configuration space quantities. This is a 2D plus time problem. We have the Navier-Stokes equations that can evolve these quantities. They look like the density here, where you have dependence on configuration space as theta and phi, as well as time. And then we have some closures that are required in order to finish off our set of equations. Now, this is different from the kinetic approach, where at each point we have this extra velocity space. This becomes a 4D plus time problem. We evolve it with something called the Vlasov equation. And then our distribution functions, which are what we're evolving, is going to be this 4D plus time. So we have two spatial dimensions, our theta phi, and then our velocities associated with that. And that has no requirement on closures. So this is what we're doing is to the right. And then the overview of what we need to do in order to make this scheme. We need to reformulate our equations of motion. We need to have a Hamiltonian description. I'll explain how exactly we go about doing that. And then we need to discretize that. In addition to that, we need diagnostics. We'll calculate moments of this distribution function. And then we want to be able to build an equilibrium out of that as well. Next, we're going to need a scheme to evolve all this in. And then the things we're going to test this on, we're going to do a simple shock problem. And then we'll do a Kelvin-Helmholtz instability on the surface of a sphere. So the probably most important slide of my talk, so if you take nothing away, hopefully you can take this one away. We have a free streaming Hamiltonian, this capital H, which depends on the metric inverse, this Hij, and our canonical momentum coordinates, Wi, Wj. In this specific form, we're guaranteed that our Poisson bracket, the second line, is going to be in its canonical form. This means it's simply in the simplest form that we can take these curly brackets of functions f and g and get this right-hand side. With using canonical coordinates, we're guaranteed that our phase space is incompressible for this problem and that we have an associated Liouville theorem. And that means we have a Vlasov equation. So this is what we're discretizing as our canonical Poisson bracket. And then this is what we're evolving, our Vlasov equation. Now, you might be wondering, is this still, if we have some geometry specified by our metric, this little Hij, is that still evolving the equations we expect it to be? So the way you can go about verifying this is you can calculate the equations of motion. You can take your partials of your Hamiltonian to get your x dot and w dot, those first two lines. And then a little bit of algebra later show that it follows the equations of geodesics, this final equation here. This is our mathematical verification that what we're doing is what we think we're doing. The gamma is going to be a Christoffel symbol, and x dot are going to describe our acceleration and velocity. The Christoffel symbol, luckily, does not appear explicitly in our formulation. And this is a significant simplification because all we have to do if we go back is just these few sets of equations rather than having to calculate these Christoffel symbols. And why these are kind of difficult to calculate, or you want to avoid them if possible, will become apparent when we go into the scheme. So one final thing we're going to need, or a few extra things, I'll mention them later, but one thing that we're going to need is how to calculate the moments of this distribution. The way we go about doing that, you integrate over your momentum space with some kernel, and you can get things like density, velocity, and temperature. Because we have these curved surfaces, we're going to end up with a volume factor, the script j, in front of our divided by our right-hand side, 1 over script j. See if I have a laser pointer. There we go. 1 over script j, and that's determined by the volume element from the tangent vectors on our space. Now, this is just something you have to keep in mind. So if you have a standard formulation like Cartesian configuration space, this will be 1. Here, it's not. But once we have this information, we can build a local equilibrium. And what we'll do with this is we're going to use it to calculate simple collisions. So the thing that we're going to discretize over is, and the scheme that we're going to use is called Discontinuous Galerkin algorithm. This is the kind of standard slide for anyone who's using DG. You've seen this before. You have your function f of x. You discretize your domain into cells. And in average code, probably the vast majority of codes involve some cell mean value. That's going to be these black dashed lines, which describe ultimately the orange curve that's passing through all of the points. A DG scheme instead has these blue lines, which more accurately describe the solution in this case. We end up matching both the mean value and the slope for these lines. So the D part is that these blue lines don't match up at the boundaries. It's discontinuous. And the Galerkin is we have Galerkin minimization, so we match the moments between our orange line and our blue lines in each cell. So it doesn't quite do justice to show a 1D scheme. You're really going to have to think that all of the functions, everything we're evolving are in 4D or higher dimensions here. So I'm going to show a 2D example. We have some function, our distribution, f of x and w, and it forms some sort of sheet on this 2D surface. And the way that we're describing this is basis expansion of this function f. So it's like a Taylor series here, where we evolve the coefficients f0, f1, f2, where f0 is going to be a mean over this sheet, f1 is going to be the slope in the x direction, f2 is going to be so on. And then you can build up quadratic terms and higher terms to whatever sort of degree you want to describe your solution in. So the final piece of physics, the final bit to our model is a collisional term. So we've added a BGK collision operator to the right-hand side. The BGK just means the form that we're taking for this collision operator. The new is our collisional frequency. We have our distribution function f, which is going to be reshaped towards our equilibrium distribution by this operation. We've chosen an operator that's both implicit, so we don't have a time step restriction on it, so we can do things like compare these models to fluid models. And then we have moment preservation, so we don't end up losing density, velocity, energy over time by doing these collisions. And a simple example I'm showing here is a 1D reshaping of a water bag distribution. So this is the initial yellow square is going after a certain amount of time to end up looking like a Maxwellian distribution. So I'm plotting out 1 collision times where you still have a mix of both states, and then after 10 collision times where it's pretty much entirely a Maxwellian distribution. So the first part of the results we're going to look at is a Sod shock test. This is simple discontinuity in both density and temperature. What we're looking at to the right is plots of the initial condition of density, velocity, and temperature, where we have a discontinuity in the temperature and density. And then we're using an exact Riemann solver to come up with a solution at a later time that we're interested in that starts to emulate the physics. Now, we want to compare and see if our Vlasov simulations look similar when we have this BGK operator to the solution we have here. But what we're looking at when we look at simulations of this distribution function f aren't really the moments. What our solution is going to look like is going to be the top row. We have our phase space distribution as functions of both our w and x, and our contours here describing how much phase space density we have at each point. You can integrate these vertically to get our density and other moments with different kernels. So you can integrate this, and you'll get the plot on the bottom. And one thing that we wanted to do to test this is, can we reproduce these results? And the answer is yes. So it might be a little hard to see on the screen, pardon me. But the yellow line here is going to agree almost exactly with our black dashed line, our exact solution to this problem. And then we can take this for a range of collisionality where this new parameter dictates how collisional we are. Nu of 15 is not very many collisions, and nu of 1500 corresponds to Reynolds number of about 2000 for you fluid mechanicists out there, where we're starting to get into the range that were described pretty well by the fluid description. But of course, the answer is going to be described in terms of these phase spaces. So you can imagine just integrating these to go from between the left and the right. Now, the final comparison that we're going to do here is going to be a Kelvin-Helmholtz instability on the surface of a sphere. We have two counter-propagating fluid elements that are passing by each other in a highly collisional limit where we are unstable to Kelvin-Helmholtz modes. And a way to kind of think of this, we have our computational domain to the right, and or to the left, sorry, where we have theta and phi, and then we can map this to the right. So I'll show you some videos on what this really looks like when we evolve it. So to the left, we have our density, our velocities in our theta direction, which is our declination angle, and then phi dot, the bottom left, our azimuthal angle, and then our temperature. So evolving this, looking at the top left, we can see the formation of our cat's eyes. These will eventually saturate at a certain limit because they can't expand any larger in the box that we're prescribing for them. And this is all the phases you really get of this instability here. And to look on the right, this is mapping the density to a physical domain. You still get this saturation. Now, these make very nice, pretty pictures, but we haven't done any science more than verification of our method to a fluid method at this point. So what sort of information can you extract from the kinetic side of things? On the kinetic side, we can take certain points on our grid. So this is our computational grid again, and I've drawn little x's for where we're going to take out parts of our distribution function. And by plotting the distribution function at those locations, we can see that in this collisional limit, they're nearly Maxwellian for most of the distributions. They might be shifted, and they might have different temperatures. But you'd say because of the symmetry of it and the kind of regularness of it, it would be a Maxwellian. You could subtract off then the Maxwellian distribution and come up with this delta F, this small change between the distribution function and our equilibrium. Now, this is where the real science resides. You can take moments of this, and you can use this ultimately in expansions to calculate what exactly things like transport coefficients, which are used to extend fluids with kinetic corrections. As well, you could compute things like closures with this in the moment routines. And these are what are the useful applications, potentially, of this research. So a summary of results, we've come up with a formalism that explicitly handles complex geometries without the need for this Christoffel symbol. If you recall, we have the surfaces. You could imagine a Christoffel symbol has a bunch of coefficients on it that all need to be expanded in the same form. So coming up with that expansion can be quite onerous. So avoiding that is a good benefit of our scheme. We have an equilibrium, and we can calculate simple collisions on the surface. And we verified our solutions to known Vlasov and fluid solid shock problems. And then finally, we've extended these kinetics to the surface of a sphere. And I'll leave it on a thanks to the CSGF for enabling all of the fun research I've done during my PhD and for introducing me to this wonderful community. And thank my advisor as well as my fellow fellows and my family. And I'll leave you with this picture of the Kelvin-Helmholtz instability on the surface of a sphere to show, we can really do a variety of geometries with this. And all you have to do is specify a different Hamiltonian. So thank you all for listening.